Good day. So before we discuss the shear and moment in beams, let us discuss the different types of beam supports. So let's have the first one. So this is a ruler. Okay, for a ruler, we'll be having one reaction. Let's say for this case, we have a vertical reaction. Okay, the next one is a hinge support, or also known as the pinned support. So for a pin support, we'll be having two reactions. We'll be having a vertical and a horizontal reaction for this case. And then the third one, this is we have a fixed support. Okay, for a fixed support, we'll be having three support reactions. We'll be having a vertical reaction, a horizontal reaction, and a moment reaction. So these are the three most common types of beam supports here in mechanics of deformable bodies, wherein we are just to discuss determinate beams. If we say determinate beams, so these beams can be solved using the three equations of equilibrium. Then let us discuss the different types of loadings. So we have the first type of loading. This is the concentrated load. Concentrated load, or also known as the point load, since it is a type of load acting on one point. Then the next one, this is a uniformly distributed load. A uniformly distributed load, or also known as the rectangular load. Since its shape is rectangle. For some cases, if we are to analyze the beam, we need to compute for its single equivalent load. Let's say this is capital W. How do we compute for the single equivalent of this uniformly distributed load? That W will be equal to the uniform load multiplied by the span. So let's say that is omega times L. It is assumed that this single equivalent of the uniform load will be acting on the centroid of this area, the area of the rectangular loading. For this case, we may assume that it is at a distance L over 2. And by the way, for a rectangular loading, since this loading is horizontal, it is assumed that its degree is a 0 degree loading. And then the third one, this is the uniform varying load. A uniform varying load, and if it is a straight line, this is a first degree. So sometimes it is called as the triangular loading. How do we compute for its single equivalent force? Let's say W, or capital W. This capital W will be equal to, that is the uniform load, or the uniform varying load, multiplied by its span, that is multiplied by the length divided by 2. And it is assumed to be acting on the centroid of this triangular loading. If it is a triangular loading, so it is assumed to be acting on its centroid. So this distance is L over 3. While distance from the left will be 2/3 of L. If we are to observe, in the computation of the single equivalent forces of these two loadings, on the rectangular load, that is the uniform load, this is the uniform load times the span. On the triangular load, that is the uniform load times the length divided by 2. Basically, if we are computing for the single equivalent force of a given loading, basically that is equal to the area of the load. Let's say L dash D, that is the load diagram. As you can see on our rectangular loading, that is simply the height times the length, or that is the height of the rectangular load times the length. In the same way, on this triangular loading, that is the same as 1/2 of the base times height. 1/2 of this magnitude, or the highest value of our varying load, let's say the omega multiplied by the length, that is divided by 2. So basically, if we are computing for the single equivalent force of this type of these types of loading, that is basically equal to the area of the load diagram. Now, if on the last type of loading, we have the this is the applied couple or the moment. Alright, so let's now discuss some of the basics of shear and moment in beams. Okay, so let's have an example. For example, we have this beam loaded as shown. We are required to draw the detailed shear diagram and the moment diagram. Okay, for this example, I'll be using a sign convention that is for clockwise moments to be positive, and let's say counterclockwise moments will be negative. You may use the opposite sign convention. Okay, that's fine as long as you are consistent with your sign convention. Okay, first is we are to determine the support reactions. Let's say this is the support reaction at A, assumed to be upward. The same with the reaction at D, also upward. So we may do here a summation of a moment. Summation of moments at A equal to 0, assuming clockwise moments to be positive. So we have the 14 kilonewtons. This is 14 kilonewtons. How far from point A we have that is 2 meters, plus the 28 kilonewtons multiplied by 5 meters, minus the reaction at D, the span of the beam. It is 7 meters is now equal to 0. So computing for the support reaction at D, we have that as we have 14 times 2 plus 28 by 5 meters to be divided by 7. So we have the reaction at D is equal to we have 24 kilonewtons, and it is upward. So this will be the reaction at D. Now computing for the reaction at A, we may do summation of forces vertical equal to 0, assuming upward forces to be positive. So we have reaction at A minus the 14 kilonewtons minus 28 plus the reaction at D is 24 kilonewtons, and is equal to 0. So we have now the reaction at A is now equal to, that is the same as we have 24 minus 14 minus 28, then negative 18, then transpose, that will be positive 18. So this is 18 kilonewtons, and it is also upward. So these are our support reactions. So we have the support reaction at A. This is 18 kilonewtons upward. The reaction at D, we have 24 kilonewtons also upward. So if we are now to draw that shear diagram and moment diagram, we may first establish our shear equation and moment equation per segment. That is one way. Let's say one way to draw or give the details of our diagram. So let us first consider our first segment. Okay, let's say segment AB. Let us assume that we are to cut a section between points A and B. So let's say cutting a section at segment AB. This is for the value of x, or the interval 0 is less than x and less than 2 meters. Since if we are to go back on our load diagram or the beam, AB is a segment 2 meters long. If we are to cut a section, what will be the direction of our internal forces or the internal shear? So our internal shear on the left side will be downward, and we'll be having a counterclockwise moment. While on the opposite side of the cut section, let's say this is on the right side. Okay, for equilibrium, we are considering the opposite directions. So we will be having a shear that is upward and a moment that will be a clockwise moment. Alright, so let's say this cut section is, let's say, point E. How do we compute for the first one? The shear. So the shear for segment AB, we can have it by summation of forces vertical equal to 0, upward forces to be, assumed to be positive. So we have, that is the reaction at A, that is 18, less. The shear, V, is now equal to 0. So we'll be having the magnitude of shear for segment AB is simply equal to 18 kilonewtons. Okay, so this is for the value or for the interval 0 is less than x, less than 2 meters. Now, if we are to assume that this cut section is at a distance x, okay, or point E is at a distance x from point A, so for the moment equation, we are to do summation of moments. So for the summation of moments at point E, that is the cut section equal to 0, assuming clockwise moments to be positive. So we'll be having, that is 18 multiplied by the distance x minus the moment at the cut section, or that is m, is now equal to 0. So we'll be having, let's say our moment equation, the moment equation is simply equal to 18 of x. So this equation is applicable for the interval 0 is less than x, less than 2 meters. So if you are to input these details on our diagram, for segment AB, starting from 0, what is the magnitude of the shear at A? That is the reaction at A. So from 0, we are going up, up to a magnitude of 18 kilonewtons. Based on our equation or shear equation, for the magnitude of shear for a segment, 0 is less than x, less than 2 meters, we have a constant shear equal to 18 kilonewtons. So constant, that is a horizontal line. So horizontal line is a graph with a 0 degree, or it is a 0 degree graph. What about the moment? So what will be the moment at segment AB? So we are starting at 0. So for example, we are to consider a point just before point B. Let's say that is approximately, let's say approximately the value of x is almost 2 meters. What will be the magnitude of the moment? The magnitude of the moment will be 18 times 2 meters. We'll be having a moment equal to 36. This is 36 kilonewton meter. Okay. So if you are to observe on our shear diagram, we have the graph of the shear diagram is, let's say n, that is the degree of the graph, is a 0 degree. As we go down, we are to increase our graph, or we are to increase the degree of our graph. So we are to add 1 degree. So obviously we have A is a simple support, or at point A is a pin support, that is a 0 moment. Then, what will be the magnitude of the moment? This is basically, if we are to specify, this is the moment at point B. Okay, the 36 kilonewtons, since that is at a distance of 2 meters. So this is a 0 degree shear diagram. So the moment diagram will be first degree graph. So the degree of the moment diagram should be first degree. So that is from 0. As you can see, we have a positive shear. If you are to recall on our analytic geometry, what is the slope of a positive value, or what is the appearance of the line with a positive slope? So if we have a positive slope, that is upward to the right. So this is a positive slope, and downward to the right is a negative slope. Take note that when it comes to the moment diagram, the slope of a moment diagram is equal to the magnitude of the shear. So if you are to observe, our shear is positive 18. So that will be a positive slope. So starting from 0, okay, we will be having a magnitude of moment that is a first degree graph. And the magnitude of the moment at point B, this is equal to 36 kilonewtons. Okay, that will be for segment AB, or the moment for segment AB. Okay, then we proceed to our next segment, that is for segment BC. Okay, for example, we are to cut a section, okay, between points B and C. Okay, so considering now segment BC, that is for the interval, or yes, for the span of the beam, that is 2 less than x less than 5 meters. So let's say, okay, if we are to compute for the internal forces or internal reactions, we have the shear on the left side will be downward, that's our B, and a counterclockwise moment M. Let's say this cut section will be point F. Okay, how do we determine the magnitude of the shear for this segment? Again, all we have to do is we do the summation of forces, vertical equal to 0, assuming upward forces to be positive. So that will be the reaction at A, 18 kilonewtons. We have a downward load at point B, that is 14, minus the shear is now equal to 0. So we'll be having the magnitude of the shear for segment BC, 18 minus 14 is, we have 4 kilonewtons. This is for the interval 2 meters is less than x, less than 5 meters. For the moment equation, if we are to assume this 14 kilonewtons will be at a distance from point F, that is, this is 2 meters from A to B. So this will be x minus 2. All we have to do is the summation of moment at point F equal to 0. I'll be using black pen. We are doing summation of moment about point F equal to 0, clockwise moments to be positive. So what are the positive moments? We have that reaction at A, this is 18 for a distance of x, minus the 14 kilonewtons for a distance of x minus 2, then minus the moment at point F is now equal to 0. So we'll be having a moment equation. A moment equation that is equal to 18 of x minus 14 multiplied by x minus 2. This is for the interval of 2 less than x less than 5 meters. Now, if we are to put these details on our diagram, again, what is the shear or the magnitude of shear for this segment? This is segment BC. The magnitude of the shear will be 4 kilonewtons. On this segment, from a magnitude of positive 18, we go down to positive 4. So a constant value of positive 4 for the segment BC. So again, this is also a 0 degree graph. A magnitude of 4 kilonewtons. What about the moment? What will be the moment at for this segment? If we are to consider this one, what will be the moment at point D. We are to consider what point is that? Our next reference point, point C. Let's say we are to determine the moment at point C, wherein let's say the value of x is just before point C. Let's say the value of x is approximately 5 meters. That will be the moment at point C. The moment at point C is, we have 18, this is multiplied by 5, minus, we have 14, this is multiplied by 5 minus 2. So we'll be having the magnitude of moment about point C. That is, we have 18 multiplied by 5 meters, then minus 14 multiplied by 5 minus 2 meters. So we have the magnitude of the moment at C will be equal to, this is now 48 kilonewton meter. Alright, so if we are to place that on our moment diagram, so from 36, we're going to a value of 48 kilonewtons. So again, our shear diagram is 0 degree. So therefore, our moment diagram should be first degree. So from 36, we're going to a value of, let's say this is positive. Let's say this is positive 48 kilonewton meter. That will be the value of the moment at C. And again, this graph should be a first degree since your moment, your shear diagram is 0 degree. That will be the shear and moment for the segments BC. And for our last segment, okay, so for our last segment, this is for segment CD. For the interval 5 is less than x is less than 7 meters. So we assume that cut section will be at a distance of x. Then the direction of the shear for this point will be downward, and we have a counterclockwise moment. Then we assume this point to be, let's say point, this time, point G. So we are now to determine the shear for this segment. All we have to do, again, summation of forces vertical equal to 0, upward forces to be positive. That is, we have 18 kilonewtons, minus the 14 kilonewtons, minus 28 kilonewtons, then minus the shear will be equal to 0. What will be the equivalent of the shear for this segment? So that is, we have 18, then minus 14, minus 28. And that is equal to, we'll be having a value of negative 24 kilonewtons. So this is for the interval. We have 5 is less than x, or less than 7 meters, or that is for the segment CD. And then for the moment, let's say this 28 kilonewtons is at a distance of x minus 5. And again, for the 14 kilonewtons, this is at a distance of the x minus 2 meters. So we are doing the summation moment, or the summation of moments. The summation of moments about the cut section point G equal to 0, assuming clockwise moments to be positive. So we'll be having, this is 18 times x, minus, we have 14 multiplied by x minus 2 minus, this is 28, okay, multiplied by x minus 5 equal to, and then we have that internal moment m, which is counterclockwise, is now equal to 0. So we'll be having the equivalent of the moment for this segment is now equal to 18 of x, and then minus, okay, the 14 multiplied by x minus 2 minus 28. This is multiplied by x minus 5. So this is for the segment. Okay, for the segment, 5 is less than x, okay, less than 7 meters. And now we are to apply or to write these details on our diagram. For the segment CD, our shear is equal to negative 24. So from positive 4, we go down, okay, to a constant value of, let's say the shear is, okay, negative 24 kilonewtons. So, okay, starting at point D, okay, we have an upward reaction of 24 kilonewtons. So that is negative 24 plus the reaction, that is positive 24, that will give us, alright, that will give us a value of 0 for our shear diagram. So that is one way to check if we arrive with 0, which means the beam is in equilibrium. Okay, we have a correct shear diagram. So this will be our shear diagram. And lastly, our last reference point or specific point on our beam is point D. What will be the magnitude of moment at that point if we are to use that equation or the moment equation? So that is, let's say that is at a value of x, let's say a point just before point D. Let's say the value of x is approximately equal to 7. Okay, let's say just a point before point D. Let's say this is now the moment at D is equal to 18. This is multiplied by 7 minus we have 14. I multiplied by 7 minus 2. Okay, minus we have 28 multiplied by the quantity 7 minus 5. What will be the magnitude of this moment at point D? Okay, we have that as 18 multiplied by 7. Okay, less 14 multiplied by the quantity, we have 7 minus 2. Then minus, we have 28. This is multiplied by 7 minus 5. And that is equal to, okay, the moment at D is equal to 0. As you can see, that is a simple support or a roller support. It is expected that the moment is 0. And again, we have a 0 degree shear diagram. So therefore, our first degree will be, our moment diagram should be first degree. And this is a negative shear. As you can see, if we have a negative shear, okay, negative shear, okay, is the same as negative slope of the moment diagram. Okay, from our analytic geometry, that is, a negative slope is a line drawn downward to the right. So this is from 48, okay, to 0 at moment at point D. So, okay, this is our moment diagram. Okay, so this is our detailed moment diagram for this beam. And this is our solutions. And now, if we are already familiarized our procedures in drawing the shear and moment diagram of a given beam, okay, we may use the shortcuts. So we may have the shear or the detailed shear diagram or the moment diagram by simply inspection. So let's say, let's start with our shear diagram. Okay, so we have starting on the left end. Okay, we are starting at 0, but we have at A, we have the reaction at A is equal to 18 kilonewtons, and that is upward. So from 0, we are going upwards. Okay, to a magnitude of 18 okay, a magnitude of a shear of 18 kilonewtons. As you can see, okay, if we are to observe the span AB, we don't have a load on the beam for that segment. So which means we are to maintain this value, okay, 18 kilonewtons, so that will be horizontal. And since we don't have a load on the beam, this is a 0-degree graph, or simply a horizontal line. Then all we have to do is do the summation of forces. At this point, we have the magnitude of the shear is already 18 kilonewtons, and it is upward. Now we have at the beam, or on the beam, we have a load of 14 kilonewtons. We do the summation. That is 18, okay, minus a downward load 14 kilonewtons. That will give us a value, okay, 18 minus 14, that is positive, okay, positive 4. And again, for the span BC, we don't have a load on the beam. Then we are to maintain this value of shear, 4 kilonewtons, up to point C. Okay, so we are to maintain this value. This is constant, 4 kilonewtons for segment BC. So again, at point C, we have a load of 28 kilonewtons, and it is downward. So we do the summation. That is 4 kilonewtons minus 28. That will give us a value. Okay, what is 4 minus 28? This is obviously negative 24. Let's say this is equal to negative 24 kilonewton meter. Then we are to observe again our segment CD. We don't have a load, so we are to maintain this value of shear. This is negative 24 kilonewtons. So for segment BC, this is a 0-degree graph, 0-degree graph. Then at point D, we have a support reaction of 24 kilonewtons, and it is upward. So we do the summation, that is negative 24 plus the support reaction positive 24, that will give us a value of 0. So this is how we draw our detailed shear diagram by inspection. If you are to observe that, if you are to establish first, our equation will be time consuming. Then what about for the moment diagram? So let's say for our moment diagram, we can have the values or the magnitudes of the moments on our specific points. Considering that the value of the moment, is basically equal to the area of the shear diagram. All we have to do is specify our points or limits. So again, we have the magnitude of the moment is equal to the area of the shear diagram. Okay, so again, starting at point A, that is a simple support or a hinge support. Obviously, the moment at that point should be 0. So what is the area of this rectangle? That is a rectangular graph for segment AB. And again, if we have the degree of the shear diagram is 0 degree, we have n equal to 0 degree. Then for the moment diagram, our degree should be equal to 1. We increase the degree of the graph as we go down on our diagrams. Okay, so what is the area of the moment, or the area of the shear diagram for segment AB will be the magnitude of the moment at B. So that is the area of this rectangle. What is the area of that rectangle? So the height is 18 multiplied by its length is 2 meters. So we'll be having the magnitude of moment up to point B that will be equal to 36 kilonewton meter. So if this is a 0 degree graph, obviously our moment diagram will be a 1st degree graph. This is equal to with a magnitude of positive 36 kilonewton meter. Okay, then we are to consider this area above or the area of the shear diagram for segment BC. Okay, what is the area, or what is the equivalent of this area for segment BC? That is also a rectangle. So that will give us the moment at point C. Okay, but if we are to compute for the moment, at C, we should consider our reference point, that is point B. That is the moment at B, plus the area of the shear diagram for segment BC. So what is the magnitude of the moment at point B? That is 36 kilonewton meter. What is the area of the shear diagram for segment BC? That is, we have a height of 4 meters and what is the length? So again, this is 2 meters. This is 3 meters. So this is 4 times 3. So we'll be having the moment at C is 36 plus 12. That is the same as 48. This is 48 kilonewton meter. So we have a 0 degree on the shear diagram. So a first degree on the moment diagram. So from 36, I will be having a magnitude of positive 48. Okay, then these graphs on the moment diagram are first degree. And then for our last segment, how do we compute for the moment at point D? The moment at point D is the moment at point C plus the area of the shear diagram. This is for segment C2D. We have the moment at point D. What is our moment at point C? That is 48 kilonewtons plus what is our area for segment CD in the shear diagram? In the shear diagram, we have a rectangular area, but we have a negative ordinate, that is negative 24. This is negative 24 with a length of 2 meters. So negative 24 times 2 meters. And obviously, we have a moment D is now equal to 0. So again, that is a negative shear. A negative shear corresponds to a negative slope. And it is a line downward to the right. So we are to draw that from 48 to 0 at point D. And this is also first degree. So this will be our moment diagram. So this is how we draw our detailed shear and moment diagram by inspection.